Welcome back to this next video in which we are discussing ring homomorphisms and ideals. Okay, so we've now seen the definition of a ring homomorphism. It's a map between two rings which need not be bijective, but which is compatible with the addition and multiplication laws, and which sends the multiplicative identity in the first ring onto the multiplicative identity in the second ring. Okay, what we now want to do is see some examples of ring homomorphisms. I'm going to show you two examples of ring homomorphisms, both of which are really important. Okay, so the first one I want to show you is the evaluation of polynomials at a certain point. Okay, so it's going to be a ring homomorphism between a polynomial ring over a ring and the ring which it's over. Okay, so let's say we've got some commutative ring R. Then in the previous video in this playlist on ring theory, we discussed the construction of the ring of polynomials in the indeterminate X over the ring R. R square brackets X, like so. Okay, and we saw that as a set, this is the set that consists of all symbols which are polynomials. Okay, so explicitly written things like this: a0 plus a1x plus all the way up to some an x to the n, like so. More discretely written, the sum over I of ai xi, where these ai's are all elements of the ring capital R. Now remember, initially when you define this great big set, these things are just symbols. Okay, you should not see this addition initially as being an addition. It's just an addition symbol. Okay, this is just a great big symbol. What you've done is taken this symbol x, you've stuck elements of the ring in front of the different powers of x. So this is effectively x0, this is x1, all the way up to some finite xn, and then you've stuck plus symbols in between them, but you have just created a great big symbol here. Okay, initially that's the way we view this set. It's just a bunch of very complicated symbols. The polynomials formally are just symbols. Okay, and I should stress that when we have it written like this, only a finite number of these coefficients in front of the powers of x can be non-zero. Okay, so you don't want this going on and on and on forever. You can't, for instance, put 1 in front of every single x. Okay, that's not something that we do in algebra. It's something that you can start to think about in analysis, but we're not doing analysis, we're doing algebra. Okay, so in algebra we insist that only a finite number of the coefficients in front of the powers of x are non-zero and all the rest are just zero. And usually when we write these things out explicitly, we don't bother actually writing the terms which just have 0 in front of the power of x. We just put the powers of x which have a non-zero coefficient. Okay, so this is R of x as a set then. Okay, now to turn this actually into a ring then, we need to define an addition and a multiplication law on it. Addition is done very easily. It's just add the components. It's just done component wise. So you just add the coefficients in front of the terms, the powers of x basically, and you do that addition in the ring capital R. Okay, so if we have two polynomials, the sum over I, ai, xi, and remember this, when I write this here, again it just means construct this symbol really. It just means put these plus signs in between the terms, but it doesn't really mean a real addition. It is just putting them in between there as a symbol basically initially. Okay, and then what we'll do is define how to add two of these polynomials together, and this is the real addition now. Okay, so we'll then have another one here, the sum over I of bi x to the I, and this just by definition is the sum where this is going back to just being a symbol, the sum over I, and then ai plus bi x to the I, where this addition here is now in our ring capital R. Okay, so this is quite confusing because we've got addition just as a symbol here as part of the symbols that are the polynomials. We've got addition that we're defining in this ring of polynomials, and then we've got addition in our original ring R. Okay, so these are the real additions. These here, which we might colour in orange here, these are the fake additions, initially the fake additions. So this is a great big fake addition, this is a great big fake addition, this is a great big fake addition. Okay, right. Now, as soon as we actually define that as the way that addition works in the ring of polynomials, then these addition symbols actually become, well, they can be interpreted as being real additions, okay? Because what you can now view is any polynomial like this, you can view it as being decomposed into its monomials, okay? So you can see this polynomial, for instance, as being a0 plus a1x plus all the way up to anxn, where now this addition, rather than just being a silly symbol in between them, is actually the addition of the polynomials. Okay, so you add this polynomial to this polynomial and then get a0 plus a1x1, where now the addition is now just a silly symbol once again, and then you can go on. So you can decompose any polynomial into the addition of monomials, where you just have a single coefficient in the polynomial being non-zero in front of one power of x. Okay, right, so that's how addition is defined, and as I say, we've done this in a previous video in this playlist, so I'm not obviously in this little recap going to remind you of exactly why this obeys all of the axioms that it needs to obey to be a ring. Okay, but it does obey the axioms of the abelian group. Now, to define a multiplication on this set of symbols then, we use the fact that we can decompose any polynomial into just a sum of monomials, and then we say, okay, if we want multiplication to stand any chance of being a valid ring multiplication law, then it's going to have to obey distributivity. So if we're considering what one polynomial here, the sum over I, AI, xi, multiplied by another polynomial, which we'll have here, the sum over j, bj, xj, here is. Okay, what we can do is we can decompose both of these into their monomial sums. Okay, and when I'm doing this, I'm effectively thinking of these sums from going from being just the silly sums, where it's just a symbol, so sums that are underlined in orange, to sums that are real, sums in terms of the ring, i.e. Red sums rather than orange sums. Okay, so I've decomposed these now into their monomial expressions. They're decomposed them into sums of monomials, so they're now red sums here. And then, of course, we can just apply distributivity. So we can say if we want multiplication to distribute over addition, there's only one way this can work. You have to take every monomial here, multiply it by every monomial here, and then add them all together. Okay, so this is going to have to equal the sum over I, the sum over j, ai bj, x to the I plus j, and I've missed out a step in this definition of multiplication. Okay, so yes, we do indeed decompose them down into monomials, but the step that I've missed out is telling you how to multiply two monomials together. Okay, so definition, we have to define how to multiply monomials, and then as soon as we define how to multiply monomials, because addition allows us to decompose any polynomial into a sum of monomials, and we want the multiplication to obey distributivity, everything else is instantly defined from that. Okay, so how do we multiply monomials? So if we have ax to the I multiplied by bx to the j, then the way we define that multiplication of the two monomials is just multiply a and b together in the ring. Okay, so you multiply the two coefficients together in the ring, they're multiplied together in the ring, and then you just take the powers of x and add them together, so x to the power of I plus j. So here you can see that we've just taken every monomial from here, multiplied all of those monomials together, and now we're just summing them all up. And this again, these two sums here are sums in the ring definition of sums here, the polynomial ring definition of sums, so the red sum rather than just the silly sum. Okay, so in principle, you could then go through and add up all of these monomials and get then some final polynomial where you've just got the additions as silly sums, the symbolic sum, and then you'd have your answer. Okay, but because it's easier not to actually do that final bit, you can, of course, get an expression for what this actually is in terms of a silly sum here. Okay, but it's not actually that helpful to get it in that form. For proving theorems, it's far easier to think of the multiplication as being in this this former step, this step before you actually get to the final answer. Okay, the form that you could use to get to the final answer. Okay, this is actually a far more workable form than the final form. So I won't even go there with the final form. Okay, so here's how we add and multiply polynomials together. Okay, so to see an important example of a ring homomorphism then, our first example of a ring homomorphism, we're going to have a homomorphism, phi, which is going to map our polynomial ring r square brackets x onto the ring capital R here. So it's going to map the polynomial ring onto the ring which it's a polynomial ring over. Okay, now how is this going to work? Well, it's going to work by evaluating each polynomial as a certain element of the ring. Okay, so what I'm going to do is I'm going to take some alpha from the ring capital R. So you pick any element from this ring capital R, any one that you want. Okay, and we're going to then create this homomorphism which will be called phi sub alpha, like so, which is going to be a homomorphism from the polynomial ring to the ring capital R. Now it's not going to be an isomorphism, most certainly not. Okay, it's going to be a homomorphism, it's not going to be bijective. Okay, so the way then that this is going to work is it's going to take any polynomial, so let me take in a polynomial, sum ai xi. Okay, now you can think of this as the silly sum here. So this is orange sum here. So here is our polynomial from our polynomial ring. And where's it going to map it? It's just going to map it to the sum over I of ai alpha to the I. Now what does this sum here now mean? This sum now means the sum in the ring capital R, so green sum here. Okay, so you're summing all the terms together in the green, in the actual ring capital R, and the multiplication here actually means multiplication in the original ring capital R, and alpha to the I just means multiply alpha by itself I times. Whereas of course multiplication here in the polynomial where you had a coefficient in front of x to a power, that didn't mean anything, that was just a symbol. We just stuck the element of the ring in front of that. The x to the power was just a placeholder basically, it was just a symbol which was a placeholder, it was nothing more. Okay, whereas now we've suddenly made this mean something. Okay, so don't underestimate what we've done here. We've changed this big style. You might find this very sort of like trivial, but it's because you've always thought of polynomials in this way, that x was just a variable from the ring. Okay, but we were looking at polynomials in this formal way where x was just a symbol, it was just a placeholder, the different powers of x were just placeholders. Okay, and we defined addition and multiplication in this abstract way. Okay, right, so what we now want to see is that this is indeed a homomorphism. Okay, so the first thing to say is that this is absolutely not going to be bijective. Okay, you're going to have lots of different polynomials in here being mapped onto the same answers over here. Okay, yes, it is going to be surjective, but it's not going to be injective. However, it is going to obey the properties of a homomorphism, so let's now go through those properties. So firstly, we'll start off with addition. Okay, so what we want to check then, and I think I'll go over onto the other side for this then, we want to check that it doesn't matter whether you firstly add the two polynomials together and then map them using this homomorphism to be, or whether you first map them and then add them together in the codomain ring. Okay, so let's think about this. So what we're going to do is we're going to take two polynomials. So I have these two polynomials here, so sum over I, ai, xi here, and we'll have them added together, sum over I, bi, xi. So here's my second polynomial here. And this addition is going to be in our polynomial ring, so this is red addition here. Okay, and remember these additions here are currently just the silly additions, the symbolic additions. Okay, so orange additions. Now, what we want to prove is that this will split up. To prove is that this is equal to phi of alpha of the first polynomial, sum of I, whoops, not alpha there, that should be an A, ai xi, plus the, and I've missed it off again, I've made another mistake, let's try and repair this, phi of alpha of the polynomial, the sum over I, bi, x to the I, like so. Okay, where this now is the summation in the codomain ring, so this will be green addition here, okay, because the codomain ring for this ring homomorphism was our original ring, capital R, and we're denoting addition in the original ring by green. Okay, right, so let's firstly take this left-hand side here and try and understand why it's going to be equal to the right-hand side here. Okay, so the left-hand side then, left-hand side, if we want to add these two polynomials together, then we know how that works. We just add it component-wise, so this will become the sum over I, and we just add together all of the coefficients AI, BI, AI and BI, and we add them together in the original ring, capital R. So these additions are going to be in the original ring. However, this addition here, this sum, is still just the abstract sum. It's just that symbolic sum. Okay, right. Now, if we want to take phi sub alpha of this thing, all that's going to become is we're just going to evaluate this at alpha. So this polynomial will now become the sum over I, AI plus BI, and then we'll have alpha to the I here there. And remember now, this great big sum here is now in the green sum. Okay, it's the sum in the codomain ring here. And the multiplication here is all in the final ring. Taken to the power of I, that's all in the final ring. Everything now suddenly has a meaning in our initial ring. Okay, so that's the answer on the left-hand side here. Now let's consider what the answer will be on the right-hand side. Okay, so on the right-hand side, we're doing phi alpha of this polynomial here, and of course that's going to be, well, firstly let's just remind ourselves that that's abstract addition here, symbolic addition. And phi sub alpha of this is just going to be equal to the sum over I, AI, alpha to the I, like so, where now we've gone into green addition. So this is addition in the actual ring, capital R. This is multiplication in the ring, capital R, taking to the power of I. That's in the ring, capital R. And then we're going to be adding this in the ring, capital R, to phi sub alpha of the summation over I, BI, x to the I. Okay, so what then is phi sub alpha of this thing here? Okay, well, again, we're just going to be taking this polynomial, which again is one of these abstract polynomials, a formal polynomial, so this sum is just symbolic sum. Okay, and we're going to be mapping it onto what it is in the codomain ring, capital R. So this will just be BI, and then we'll have alpha to the I here. Okay, now of course that sum is done in our ring, so it will be green sum here. So this will be multiplication in the ring, and this will be taken to the power of I in the ring. Now of course these two things are going to be equal to one another because in the ring we can apply distributivity here. So to each of these terms here, this is multiplication in the ring, so we can quite easily split this up into the sum over I of AI alpha to the I plus BI alpha to the I, like so. So that's just applying distributivity in the ring, capital R, the fact that multiplication distributes over addition in the ring, capital R. And then of course it doesn't matter what order we add things together, we have associativity and commutativity of addition in a ring, so we can easily split these two things up into these two separate sums, like so. So this will be equal to this. So indeed we have shown that this homomorphism criterion this mapping satisfies the first homomorphism criterion. Now let's turn our attention onto the second homomorphism criterion, the compatibility of multiplication. Okay, so what we now want to prove is that if we take phi sub alpha of two polynomials multiplied together, so let's have a polynomial, the sum over I, AI, x to the I here, and then another polynomial, the sum over j, bj, x to the j here, so two polynomials. We want to prove that this is equal to phi sub alpha of the first polynomial here, the sum over I, AI, x to the I, and then we want it multiplied by phi sub alpha of the second polynomial here, which will just be the sum over j, bj, x to the j. Okay, so we want to prove that this statement is going to be true. We want to prove that multiplication is compatible between the two rings. Okay, right, so let's take the left-hand side once again. Now, of course, we're starting here with two abstract polynomials here. So these are initially abstract sums, okay? Now, the way that we multiply two polynomials together in our polynomial ring is we firstly instantly say, okay, let's decompose them into their monomial sum. So we'll go from viewing these in the orange sense of the sum to the red sense of the sum, okay? And then what we'll do is multiply every single one of the monomials and get a massive great sum of monomials in the polynomial ring. So this will become the sum over I, the sum over j. We'll multiply the coefficients together in the ring capital R. So AI and BJ here are being multiplied together in the ring capital R. And then we'll get this in front of x to the power of I plus j, like so. And I remind you that this great big sum over I, sum over j, that's a monomial sum. You're adding up loads of monomials, so it's addition in the polynomial ring. Okay, and now what we want to do is take phi sub alpha of this thing. Okay, so this is a great big sum of monomials. Now, what we have proven so far is that if you have the sum of two separate polynomials like this, where the sum is being done in the polynomial ring, okay, then we can split it up. It becomes phi sub alpha of one polynomial plus the other polynomial. We have got such a thing. We've got a great big sum of loads of monomials, okay, and we've done this for two separate polynomials. Of course, it will extend. As soon as it's true for two polynomials, it becomes true for an arbitrary finite length of polynomials, which this is going to be an arbitrary finite length of polynomials. Okay, so what we can now say is that this will equal the sum over I, the sum over j of phi sub alpha of these separate polynomials, okay, where this now is addition in the final ring, green, okay, because look, I've turned addition in the polynomial ring into addition in the final ring. I've just done it for an arbitrary length of things rather than just two things. Okay, so this will become the sum over I, the sum over j of phi sub alpha of these monomials, and of course those monomials will just be ai times bj multiplied together in the ring, and then we'll have alpha to the I plus j, where now this multiplication means something in the ring, and raising to the power of I plus j means something in the ring here. Okay, but of course that's exactly what you would have got if you took these two sides, well, if you went to the right-hand side here and worked out what the right-hand side would be equal to. So if we take phi sub alpha of the sum over I of ai x to the I, then by definition what that's going to be equal to is the sum over I of ai alpha to the I. Okay, so initially, of course, this addition, and indeed we'll get ahead of ourselves, this addition here were symbolic addition. Now we're turning them into addition in the ring capital R. This is multiplication in the ring capital R. This is raising to the power of I in the ring capital R. So that's phi sub alpha of the sum over I, ai x to the I. Now if we look at phi sub alpha of the sum over I, bj x to the j, exactly the same thing holds true here. We'll turn this into the sum over I, or rather the sum over j, bj alpha to the j here. Okay, where this is a great big sum done in our ring capital R, and this multiplication is done in R, and this taken to the power of j is done in the R, ring R. And now, of course, what we can do is just multiply this out in the ring capital R, because distributivity is true there, and of course it would just become equal to this great big sum here with a tiny little bit of manipulation. Okay, so indeed we have satisfied the multiplicative criterion. Okay, the final thing that we then need to look at and check is that the multiplicative identity in our polynomial ring is mapped onto the multiplicative identity in our codomain ring, capital R. So we need to make sure that phi sub alpha of 1 is equal to 1. Okay, well, 1, the multiplicative identity in the polynomial ring, that is just the polynomial where you have 1 as your term in front of x to the power of 0 as the constant term effectively, and then 0 as the coefficients for all the other powers of x. Okay, and of course when we evaluate that at alpha, it is just going to equal 1, so indeed the multiplicative identity in our polynomial ring will be mapped onto the multiplicative identity in our ring. Okay, so there is a nice example then of a ring homomorphism, and it's one that's going to become very important as we progress through ring theory. Okay, so we'll have a break there and then we'll look at another very important ring homomorphism in the next video.